Welcome to a course on low-level programming. In today's lecture we'll talk about compilation and optimization, so how to translate code written in a high-level language such as C into code your machine can execute, and how to generate code that runs efficiently. So my name is Michael Engel. I'm also teaching the compilers course here at NTNU, and if you're interested in topics like these, I'd be happy to meet you again in an upcoming semester. So in the previous lecture, you've seen an introduction to C and specifically to C pointers, how to use them for grouping different data types together in structures, how to group identical data types together in arrays, how to use arrays of characters as a representation of strings in C, then how to write generic functions using pointers in C, and how to do memory management in C in general. Today, we'll take a closer look at how the compilation process for your C code works. And after an introduction, we'll first take a look at the different parts of a compiler. So how do these parts interact? How does the compiler tool flow work? Then we'll dig into details of the compiler stages. So the first stage for C compilers is pre-processing, which is macro processing and text replacement. Then the compiler itself starts, so the compiler is split into two general larger parts, the front end and the back end. So the front end is concerned with lexical analysis and syntactic analysis, so scanning and parsing, so chopping up your text, your program text into separate parts, looking if they fit into the structure your programming language grammar prescribes. Semantic analysis checks if all your variable types fit together. And the result of your front-end processing is a so-called intermediate representation, and this intermediate representation is then used by the backend to generate machine code. So this generates the real code that's executable on the machine, and there are different stages to optimize that code. And after this, we'll take a detailed look at some of the common compiler optimizations, how they work, what you can achieve with these, and finally, we'll take a look at the remaining parts of our compilation toolchain: assemblers, linkers, and loaders. So let's start with an overview. If you write a larger C program, you don't write your complete code in one single C file, but you try to split it up into so-called compilation units. So these compilation units are provided to achieve some level of modularity, so you can hide certain things inside of such a compilation model unit. So you can make certain functions or variables available or unavailable to other C code in your complete program. And each of these compilation units commonly has a main file, a C file, which contains its source code and optionally a number of header files, and these header files declare public interfaces of units, so which functions, which variables are accessible from other compilation units in your complete program. In C, this is different to Java, for example. Each compilation unit is compiled separately, and the output of this compilation process is a so-called object file, which contains relocatable object code. Relocatable means that addresses for variables or addresses for branch targets in your code are not fixed, but they are supported with hints, and these hints have to be used later on to translate these relocatable addresses to real fixed addresses in your final binary. This also allows the creation of object code libraries, so when you've written a function or a set of functions to, for example, draw graphics or do cryptographic functions, you can put them together in a so-called object code library just containing machine code instead of source code, and you could deliver it to your customers so they could just reuse your functions. So if each compilation unit is compiled independent of all the other C files in your project, there needs to be a part knitting all these parts together, and this tool is called a linker. So a linker takes all these open references. For example, we call a C function in a different file in a different compilation unit. And so a linker is responsible for knitting all these together, for tying these together, so all the references are resolved before you can create a final executable binary. And this executable, so called a .exe file on Windows, for example, or in Linux it's an ELF file. This is then finally the program you can execute. However, this program is not necessarily one that contains everything that's needed to execute it. So modern operating systems contain so-called shared libraries or DLLs on Windows, and these DLLs are delivered with the system and implement certain functionality, like for example a cryptographic function. And these DLLs are provided with the operating system, so you don't have to deliver them with your application. So in turn, when you load an application and this application references some of these shared libraries, the operating system is responsible for adding these shared libraries when you start your program to the binary image of your program in memory. And the tool of the operating system that does exactly this, so knits up all these references, ties up all the loose ends, let's say, for functions referenced in a shared library. This tool is called a loader, and this loader also initializes data areas, so you have a concrete state that you can start working on. When you write C code, you need to declare and define functions and variables. So what's the difference between a declaration and the definition of a function or a variable? A declaration is used to tell the compiler that somewhere in our program exists a variable or a function with a certain name that we intend to use. So for example, this declaration here declares that somewhere in our code there is a function with the name swap. This takes two parameters, which are pointers to integers, and we have given them names here. These are not absolutely required because the compiler in a declaration only cares about the types, so it would be sufficient to write int pointer, int pointer. And it also tells the compiler that swap doesn't deliver any return value by giving a type qualifier of void here as a return value. In a definition, you provide the implementation of a function, so the function body, and possibly allocate memory for local variables and so on. So when we want to define, so implement a function swap, we have the same prototype for our function here, so it's void swap, so we don't return a value, and it takes two integer pointers as parameters. And since we want to access these integer variables here that are passed to our function swap, we need to give them names now definitely. So the first parameter is given the name A, the second one is given the name B. Both are local variables to our function swap, so names A and B are local to our function and not available anywhere outside of this function. And then our function body can come here and implement our function by swapping these values using a temporary variable. So let's look at an example for compilation units. We have a header file that defines and declares an integer variable arraylang and declares a variable max size to be of type integer, but it's not defined here. That's indicated by the keyword extern, so this tells our compiler it's defined somewhere else. So this declaration here doesn't allocate any storage space for a variable. This declaration up here does allocate storage space for an integer. And we have a function declaration. This is our prototype for the swap function we've just seen on the previous slide. So when we write an implementation in our file a.c, we have to include our header file so our compiler knows about our function declaration. And by including this header file, the compiler just copies verbatim all these lines of the text file a.h into this position here, so it replaces the line include a.h by the text of our header file. And then we can implement our function here, so we have void swap, we give our parameters the names A and B, and we have our swap function implemented here by dereferencing variables and assigning them again. So if you have problems understanding pointers and stuff, just try to see if you can simplify this function. Can you simply exchange these variables in a more simple way? If you can do it, try to figure out if your implementation is correct. So if we now try to use this swap function, we would write something like this in main.c. We could include standard.io.h, a header file for the Unix standard input and output functions. This is not strictly needed here since we don't print anything, but commonly you would want to print a result of something, and we include our header file a.h. Now in our main function we define two variables a and b to have the values 5 and 15, both are integer variables here, and then we call swap of a and b. Now if you look closely, maybe there's something wrong. So we've declared our function swap to take pointers to integers. What we pass here are integers, and our compiler is not intelligent enough to automatically provide a pointer, so it just figures out something's wrong here. We're expected to pass a pointer to an integer. We're just passing an integer, so it throws an error. So our compiler can use the prototype of our function here to figure out something is wrong. If we had not included our header file here, the compiler wouldn't know anything about the swap function. Now that doesn't mean it wouldn't compile the function. It just means it doesn't have any type information about a and b. So essentially, without knowing what a and b, what types a and b must have, our compiler would just compile this and not complain. So including the header files with function declarations with your prototypes for your functions is crucial to ensure that your compiler can type check your programs so that you have fewer errors in your program.